Solving systems of equations algebraically, we're going to look at essentially two types, linear quadratic, so a line and a parabola, or quadratic quadratic, where we have two parabolas. And remember, when you're solving a system of equations, what you're really trying to do is find points of intersection. So let's just think about the different scenarios that we can encounter. If it's a linear quadratic, we have one quadratic function, so we have one parabola, and the line might intersect the parabola in two places. That'll be pretty common. It might miss it altogether. No intersections, no solutions. Or it might intersect the parabola in one place. That could happen with a vertical line, or it could happen with a line that is just tangent. And in that case, you'll have one point of intersection. Now let's think about quadratic quadratic. That's two parabolas. And there's a lot of different possibilities here, but they all amount to pretty much the same thing. You're either going to have 2 points of intersection, 1 point of intersection, or none at all. Some of the ways you could have 2 points of intersection, you could have one facing up and one facing down, for instance. That would give you 2 points of intersection. But you can get 2 points of intersection even if they're both facing up. So for instance, you could have one facing up and then a slightly wider one facing up. That would give you 2 points of intersection. You can, of course, get 1 point of intersection if you had a parabola, one facing up and one facing down. They might just touch. However, you can also have both of them facing up. If you just take one parabola and then imagine shifting it to the right, so you have one parabola, let's say this one facing up, and then we have another one, just simply the same one but shifted to the right. That's going to have a single point of intersection as well. So there's a variety of different ways we can get 2 points, a variety of different ways we can get 1 point, and of course they might just miss each other altogether, in which case we get no points of intersection. So let's take a look at a couple of examples. We'll start with a linear quadratic. And let's say we have the parabola y equals x squared plus 1, and the line 2x minus y equal to negative 1. Now the method we're going to use here, if you recall solving systems of equations from Math 10, we looked at three methods: solving graphically, solving by substitution, and solving by elimination. Now solving by elimination was our preferred method when we were dealing with linear systems, so two lines. But while you can do that with linear quadratic, it's probably easier just to think of substitution, which means you want to solve for one variable in terms of the other. Now, we already have y in terms of x in the quadratic function there, so we could just take that expression x squared plus 1 and pop it into the equation for the line. Wherever we see y, we would replace it with x squared plus 1. What I usually like doing, though, is just simply solving them both for y. So I'm going to put the line in slope-intercept form. I'm going to bring the y over to the right-hand side and add 1 to both sides, and I'll get y equals 2x plus 1. So now I have an expression for y in terms of x squared plus 1, and I have another expression for y in terms of 2x plus 1. So if I set those equal to each other, I will find the points of intersection, or at least I'll find the x values for the point of intersection. So I can write this as x squared plus 1 equals 2x plus 1, and that's just a quadratic equation. Basically, every problem in this section is going to boil down to a quadratic equation. So you have to remember everything you learned about quadratic equations from Chapter 3. Let's bring everything over to the left-hand side. The 1's disappear, which is kind of nice, which makes it very easy to factor. We can just take out a common factor of x, and we're left with x minus 2. And therefore, we know that either x is 0 or x minus 2 is 0, which means that x is equal to 2. Now, you're not done, because we're looking for points of intersection. We've only got the x coordinates. So if x is 0, the corresponding y coordinate can be found by taking a value of x equal to 0 and plugging it into either of the two expressions that I've got highlighted in yellow. Now you should get the same value for y. If you don't, you've done something wrong. So 0 squared plus 1 is 1. 2 times 0 plus 1 is also 1. So that means one of our solutions is the point 0, 1. And then if we take a value of 2 for x, we get 2 squared plus 1 is 5, or 2 times 2 plus 1 is also 5. And so we have 2 comma 5, right? The corresponding y value is 5. So a rough sketch of what this looks like. We have a parabola, y equals x squared plus 1, that comes down, has a vertex at 0, 1, goes back up again. And the line y equals 2x plus 1 has a slope of 2 and a y-intercept of 1. So we know they both pass through that point right there, and another point over there. You can try graphing these on Desmos, and the nice thing is that you can plug in the line exactly the way it's written, 2x minus y equals negative 1, and you can see our 2 points of intersection, 0, 1, and 2, 5. Let's try a quadratic. So I'll go down onto the next page, and let's take a look at y equals x squared plus 1, the same from before, and this time y equals 2x squared plus x minus 1. So we have both expressions written in terms of y. They're both written in explicit form. That means we can really just set those two things equal to each other. X squared plus 1 equal to 2x squared plus x minus 1. It's a straightforward quadratic. Bring everything over to one side. I like to collect the terms on the side that will give me a positive x squared, so I collect them on the right. If I subtract x squared from both sides, I just have x squared. If I don't have any other x terms. If I subtract 1 from both sides, I get a minus 2. That factors quite nicely as x plus 2 and x minus 1, which gives me a couple of zeros. If x plus 2 is 0, that means that x is negative 2. And if x minus 1 is 0, that means x is 1. What are the corresponding y values? Well, I'll take my negative 2, plug it into either one of the expressions. Negative 2 squared is 4, 4 plus 1 is 5, and so that gives me one solution at negative 2, 5. And if I take a value of x equal to 1 and plug it in, I get 1 squared plus 1 is 2, and I have a point at 1 comma 2. Now let's see what a sketch of this looks like. So again, we've got the same parabola as before, y equals x squared plus 1. The other parabola is definitely facing up. Without a little bit more work, it's kind of tough to tell what's going on with it. It turns out that because of the fact that it has a leading coefficient of 2, it's been stretched out vertically, which means it's really appears narrower. And it turns out to have a vertex at negative a half. So it looks a little bit like this, with the 2 points there of intersection. This one being negative 2, 5, and the one on the right being 1 comma 2. And you can verify that again on a graphing program like Desmos, or you could verify it on your TI-83 as well. And you can see the 2 points of intersection, and the fact that the red one, y equals 2x squared plus x minus 1, is vertically stretched out means it passes there at 2 points. If we continue going up, they're never going to intersect. In fact, they'll get further and further apart. Now, let's take a look at a slight wrinkle here that'll require us to remember something from previously in the course. Let's say you have a question: for what value I'm having difficulty spelling here, but for what value of b does the following system have only one solution? It's the first part of the question. And what is that solution? Okay, so here's the system. Y equals minus 2x squared plus 3x minus 1, and then we have y equal to negative x plus b. So, here's the situation. We have a parabola that's facing down. That's the first equation. And then we have a line with a slope of -1. And so, very rough sketch. We've got something like that. And then we have a line, and we want the line to just touch at a single point. And when you do calculus, you'll actually have a completely different way of doing this question, which will be much faster and more efficient. But let's think about what we know. We've seen that whether it's a linear quadratic or a quadratic quadratic, if we're trying to solve it algebraically, we end up getting a quadratic equation. Now, this is really asking us for a value of b that'll lead to only one solution to the quadratic equation. Well, when we start talking about the number of solutions of a quadratic equation, what we're really talking about is the discriminant. So what we need to do is get the quadratic equation that we would solve, figure out what the discriminant is, and if there's only one solution, that means the discriminant is 0. Remember, if the discriminant is positive, you have two distinct solutions. If the discriminant is 0, you only get one. And if the discriminant is negative, you don't have any solutions at all. So, since they're both written in explicit form, it's pretty easy to set this up. We'll just set these equal to one another. So we have minus 2x squared plus 3x minus 1 equals minus x plus b. Again, I like to collect everything on the side that's going to give me a positive x squared. So I'll bring everything over to the right-hand side. I'll add 2x squared to both sides. I'll subtract 3x. When I subtract 3x from minus x, I get minus 4x. And then I'll add 1. So I have plus b plus 1. There's my quadratic equation. Now, I want to find the discriminant. So the a value for plugging into the quadratic formula or the discriminant is the coefficient on x squared, which is 2. The b value, which is the coefficient on x, is minus 4. And the c value, for the purposes of the discriminant, is whatever is not being multiplied by x or x squared, which is, in this case, the expression b plus 1. So if I want to figure out when the discriminant is equal to 0, the discriminant is b squared minus 4ac. Well, in this case, that means negative 4 squared minus 4 times 2 times b plus 1 equal to 0. And that's a pretty straightforward equation to solve. This is 16. 4 times 2 is 8, so minus 8b, and then minus 8 equal to 0. I'll bring the 8b over to the right-hand side. 16 minus 8 is 8. And I'll divide both sides by 8, and I get b equal to 1. So that's the first thing I've just figured out. For what value of b does the system have only one solution? When b is equal to 1. So now what I can do is I can take this equation and just simply replace the b with my solution, 1, and then I'll have a quadratic equation, and I'll solve it to figure out the actual solution. So 2x squared minus 4x plus 2, if I let b equal to 1, 1 plus 1 is 2. This, I can divide both sides by 2, or alternatively just factor out a 2. If I divide both sides by 2, it just gets rid of the 2, x squared minus 2x plus 1. And that trinomial is easy to factor, and not surprisingly, it's a perfect square, meaning that I only get one distinct root, and that distinct root is x equal to 1. I still have to find the corresponding y value. So the corresponding y value would be, if I just take x equal to 1 and plug it into either of the equations, I get negative 1 plus 1, which is 0. Or if I plug it into the quadratic, plug it into the quadratic, and I have a bit of a technical difficulty here. And okay, there we go. If I plug it into the quadratic, I get the same thing, which is y equal to 0. Now, let's try looking at this on Desmos. The really nice thing about Desmos is that you can play around with a slider, and then you don't really have to think about solving it and then graphing it, because we don't know what b is at first. So if we just let b equal to 0, we know we've got a line y equals negative x. And you can see it intersects the parabola in two places. So if we move b down, we're just dropping the y-intercept, so we're dropping the line. So it's going to continue to intersect in two places. And if we make b too big, it's going to miss the parabola altogether. We already know that b equals 1 gives us the right line. It's just tangent, and there it is, the single point 1, comma 0, which is what we verified algebraically.